So now this is this third lectures of this today's morning. It is given by Cinzia Da Via, the professor of physics in Manchester University and also visiting professor of Stony Brook. And she is an expert of the radiation detector, high energy physics and biomedical application, and also a member of ATLAS experiment. She will not talk much of the ATLAS experiment, so I will not go much detail on it. But she is also a co-author of 3D sensor and prove the radiation hardness properties are dependent on the geometry. She is a co-chair of the independent committee of EU Attract initiative to promote radiation imaging technology research across different fields of application in Europe, and the chief editor of this frontier of physics, radiation detection and imaging. So with this background, you now realize why we called her to give a talk of this technology transfer from the high energy physics to the industry and medical sector. Yeah.
Thank you. So, thank you very much. Well, actually, thank you. It's a great pleasure to be here. Actually, I am not here. I am somewhere else because it should be midnight plus for me. So you can imagine the state I'm in. So bear with me, okay? So the introduction that was made, of course, is what I did because I am an old person. And so I did a lot of things in my career and my life. The truth of the story is that I am a constant learner. And so if it's not working, of course, nah, yes, let's do that, right? So the truth of the story is that, yes, you do a lot of things, but if you can keep the passion inside you, you are a constant student. And this is the way I really prefer to define myself, someone who doesn't know, and this moment in which you start really looking into the details, realize how much you don't know. So it's a message for you as well. And so we are starting with this talk, which is going to be a little bit different than what you have seen so far. I've been asked to talk about the synergies between high energy physics, medicine, and industry. So, guys, we will have some business. We will talk about business as well, because this is something that some of you might be interested in getting into in a moment of their career. So, first of all, since we have this synergy, the very first thing that I'm going to do, since you now have seen during these 2 weeks a lot of the technologies, accelerators, particle detectors, and so on, and also these very beautiful applications, even the future that you saw in the talk just before mine, we need to identify the assets that we have in high energy physics, and then look at the requirements that those assets must have in order to be also useful for other applications in other fields, and medical applications, of course, are the most important one. And I'm showing you in a moment interesting historic examples. So the two main examples are accelerator and detectors, but I will also touch two other examples. One is going to be simulations. I only have a couple of slides, but I think it's very important. And the last one is the human capital. And again, this I think is really quite essential for all of us. So, right. Don't worry, I'm not going to enter into too many details. These slides are really a snapshot just to show through the very good moment in time. So the beginning of the last century, or the end of even the previous century, so the 1980s. And this is because everything started for all the things that we are doing today, right? So everything started here with Röntgen and the discovery of the X-rays. And what I'm going to show you, so on the top you see all the great discoveries here, you see Rutherford there, and you have Marie Curie, great lady, and the discovery of the radium and polonium. And at the bottom here is something which is, of course, very close to our heart for us instrumentalists and developers. And those are all the technologies which have been fundamental for all those discoveries. So nobody should never tell you that, yeah, detector, R&D, no, is really no second class of a theory, you know, yes, and then of course you have the experiments and all the data analysis. Detector, yeah, you have to tolerate it. It's between engineering, you know. So it's almost engineering. And I said, sorry, wait a second. No detector, no physics. And actually, I have a great example for you, just to get a little bit of diversion, because I get passionate. I just woke up immediately when I thought about that, because you hear that sometimes. Okay, you have there are new detectors which have been updating accelerators which were there, like SPS, for example. An A62, new detector with really the latest precision technology. They are doing book text physics right now. So a good detectors is really the difference between very good physics and no physics at all. So a little bit more of that. On the top, great discoveries, and at the bottom, the detectors. And you recognize here, 1934, photomultipliers. Can you imagine? They are really with us till today. Also, the reason why I showed you that is, well, semiconductor revolution, 1947, Nobel Prize, William Shockley and John Bardeen. Then, of course, you know everything about it because you've been through 2 beautiful days of presentations about semiconductor and in particular silicon sensors, how they work. So I'm not entering into this, but just for your knowledge, this here is the 75th anniversary of the transistor. So 75 years ago, all the detectors and the great instruments that we have based, and not only, what am I talking about? The computer here, the mobile phones, everything basically, transistors. And this was the very basic, and I think there is a best picture actually in this one. No, where is it? Right, that one. The so-called point contact germanium transistor. And this was the one that originally was really the very first instrument that proved the functionality of the transistor. So it is really quite a great year. So it was January, between December and January. So December 1947 and January 1948. So really a great moment. But also the reason why I showed you all this paraphernalia of discoveries and great moments and detectors is because it's going back to my point, and it is the energy transfer between the fundamental physics and the fundamental application and medical imaging here. So November 8, 1895, 1896, 1 year later, here we have this gentleman who published a book on the therapeutic use of X-rays. Can you imagine that? So it was really from the start. And here you have in 1903, there was a very first UV rays used on a patient to treat lupus, etc. But so can you really see, it is unbelievable how fast people realize that some new technology can be used in the medical sector. So here is, well, another very good and important one that I choose from these numbers, and there are really several examples, is 1931, Van der Graaf generator. There were a lot of people who contributed to that. So have a look at how Van der Graaf somehow was preceded by others who have been really putting important inputs and insights. But then in 1937, 5 years later, 6 years later, this, so at Harvard Medical School was the first to use this machine clinically to produce X-rays for the treatment of cancerous tumors with radiation. So already at that time, this was really perceived as a possible way to solve the problem with cancer. Then, of course, we have the first linear accelerator, 53, and in 56, there was the first patient treated with the LINAC. So very, very short periods of time. And then, of course, I cannot really refrain from showing you this because it's so closer to us. You have heard 2 beautiful days and 2 beautiful lectures on gas detectors. And of course, this gentleman that you see here, Georges Charpak, was the pioneer of this type of technology. And in '68, he proposed it and got a Nobel Prize in '92. In the '70s, so a couple of years later, he really used the technology for X-ray imaging with 10 times less dose to the traditional radiographic films. So again, another beautiful example on how this, the technologies and for high energy physics in particular, or fundamental science, let's do that, and medical application, they're going hand in hand. Right, don't get scared by this slide, but it is again another snapshot on the high energy physics instrumentation assets, okay? So I'm starting with the particle accelerators. Well, I will go through today particle accelerators, so there is really quite a lot to say, simply because there is really quite a lot going on with vacuum. There is really enormous applications now with vacuum. Surfaces, again, enormous application with surfaces. Just as an example, there is a very strong collaboration with people at CERN, which are treating surfaces for accelerator and LIGO, for example, for the people who are treating the mirrors of the LIGO and, generically speaking, interferometers for gravitational wave. Then you have magnets. We will enter into that in a moment. Then there is, of course, the cooling and the superconductors. Radiation detectors, huge, enormous. And there you have, of course, when you are talking about detectors, this is some sort of a jargon. It's not only the sensing part. You normally talk about the combination of sensor and electronics. So you have the sensors, you have gas solid state, scintillators, but then you also have the integration and the supportive structures. So again, I will not really have time to go on those, a lot of those. I will just touch a couple of points. Data analysis and simulations, a lot. World Wide Web, right? Everyone says that, but it is a truth story. So CERN was the place where the World Wide Web started. And now we cannot do nothing. We do nothing without it. Okay, and so again, really it is quite an important contribution in the good, alas, in the bad as well, as we know today, but to humanity. So, but then we have the theory, then we have the data library, then we have the software, then we have the big data. And big data really entering very strongly everywhere. And the transmission of the big data. So there is all really together there. Electrical and civil engineering, it's there as well, because there are tunnels. We know that the civil engineering goes into other probably very most important civil parts of the, but contributing there for several parts. But then you have the infrastructure, the power distribution, the large undergrounds, and the installations. Then we have the data acquisition systems. They go hand in hand with the data analysis and simulation somehow, because you have electronics, which is dedicated to that, all the links, the transmission, the big data again, and the triggering, and of course, a very big, no time, but very big there. It is, of course, artificial intelligence, which is now everywhere. So guys, with me a moment, because I can see that I'm losing you. Human capital is you guys here, and ingenuity, creativity, large-scale operation, coordination, education, and of course, global collaboration. In physics, so physics is one of the very few examples, with music maybe, where physicists from all over the world, from war places, they are collaborating together. It's another language, and it goes beyond even the deepest emotions. And I think this is really something that we are doing, and we should really be recognized much more. Okay, so some examples here. Synchrotron light sources, particle therapy, superconductive magnets. There are 70 in the world, synchrotron light sources, biology, medicine, chemistry, material science, and technology, particle therapy, huge, 80 working worldwide, proton therapy, okay. By 2030, it is estimated that between 300,000 and 600,000 patients will have received proton therapy treatment and be cured. Because this is the key point. With protons, you can cure. X-rays, there are problems, but with protons, and even better, carbon ions, you can. Superconductive magnets, they're not really on the radar very much, but they should be, because we are really talking here about nuclear magnetic resonance, nuclear magnetic imaging, and nuclear fusion. I won't talk about the last one because of requests, but I will mention the first two. Right, synchrotron light sources, as I said, this is an image of one of them. There are 70 working in the world. There are several around Europe. And there are several applications, as I already mentioned. So I will move on just to make sure that I'm not really wasting time. As one example of what you can do with synchrotron in the biomedical sector is the so-called protein crystallography. How is it working? You have an X-ray, so it's generated by synchrotron light. So you know about it. So I won't enter into how this is done because you had a lecture dedicated to that. So being a crystal, X-rays are going to be diffracted by the crystal orientation, so all the crystal planes, and you will have diffraction pattern, which is being reconstructed, all these dots. So for that, the crystals will need to be rotated. So you have a so-called rocking curve of the crystal. Then you have an electrodensity map, and you are with a very, very heavy computation, reconstructing the atomic model. So this is the type of image that you are going to get. This is the Bragg law, so a very simple diffraction within a medium. And here, what I really wanted to show you is the image that this lady here, Rosalind Franklin, got in 1952, and someone else got the Nobel Prize. She didn't get it. One has to say that unfortunately she died of cancer, actually, and they gave the Nobel Prize after her death. But on the other hand, she was not even being considered. And if there is a beautiful book where there is all the story about it, and well, you may say that there is some ethics to be considered there, but I won't enter into that. The difference between this image that she took, she was an amazing crystallographer, and images that you can get with the modern proton synchrotron radiation crystallography, it's really quite staggering, okay? So she was really amazing. Right, I promised superconductive magnets, and here we are. So superconductivity was discovered in 1911 by a Dutch physicist, the gentleman here, Eike Kamerlingh-Onnes. But then there were really quite several people who contributed to the studies of superconductivity and this application. All the magnets that are being used in accelerators today, they are superconductive, okay? And they are just relying on the fact that when you are cooling down to a certain temperature, normally it's working at low temperature, then you have that material, there are certain materials which they lose their material resistivity. And so they become superconducting, okay? So a coil made of superconducting material can produce stronger magnetic fields than resistive, of course, electromagnets, and the superconductive portion of most current magnets are composed with niobium or niobium titanium. This is so-called type 2 superconductivity. I let you go and look at what it means. And the critical temperature is 10 Kelvin, and the superconductors made with this material can reach a magnetic field up to 15 Tesla. And there are also other type of magnet which are made with of niobium and tin, just to put you in the structure. And this is how a magnetic resonance imaging looks like. You have two of those, a closed one, and so you have that the coil is really, the center of the coil is where people are being inserted to be then tested, and you have an open one, and this, of course, is a little bit less problematic for people who are suffering of closed space. How is nuclear magnetic resonance working? Who knows how it's working? Who heard about that before? Raise your hands. Any other? Okay. And so there are a few people. So for all the others, pay attention here. So the principle of nuclear magnetic resonance involves three sequential steps. The first is the alignment of the magnetic nuclear spins in an applied constant magnetic field, B0. The second part, which is very important for the resonance itself, is the perturbation of this alignment by an external oscillating field. Normally it's radio frequency. And then you are detecting and analyzing the electromagnetic waves emitted by the nuclei of the sample as a result of this perturbation. And you see here what happens. So this sketch, so this is a spin, okay, of any atom, any particle. And then you have that without an external field, there is a random orientation of the magnetic moment, okay, of these particles. When you apply an electric field, a magnetic field, all those, they are aligning. But then they can align either with the magnetic field or against it. And the fact that you have this double alignment is called alpha and beta, means that there is a gap between the two. Interestingly enough, when they say that you have a stronger magnetic field means better images, is because this gap depends on the magnetic field of your magnet. So the bigger the magnet, the better images and the better resolution you can get. I'll show you an example in a moment. So when you have that this external resonance that you are inducing gets to the level of the gap which is being produced, the two alignments between alpha and beta, so with and against, they start flipping. And this flipping is what is generating the signal, which is going to be used to create images or external signal that can be recorded. Okay, when these two are close in wavelengths or frequency, as a matter of fact, then they are in nuclear magnetic resonance. And so this flipping between the two is what is giving you the signal that is going to be recorded. Right, so the spectroscopy then does exactly that. You have that different nuclei, they respond differently, of course, because of their nature, to these external fields. For example, I have an example here. You have the hydrogen in a 21 Tesla magnetic field resonate at 900 megahertz. And in fact, it would just be called a 900 megahertz signal for hydrogen. Okay, but it needs to be with this condition. So you have the magnet, you have your detector, you have the external perturbance that is going to be inserted, you have the absorption, you have the emission, and then you have your signal. And this is how the spectroscopy looks like. Of course, the interesting idea that someone had, and it was among, of course, all these people who got the Nobel Prize at the very beginning of this story, is when someone realized that these really could be used in living beings and humans in particular. And this is what is being, of course, done. You have that exactly with the same principle. The person is being inserted either in this open or closed MRI system. You have the radio frequency, which is, of course, changing and resonating with the magnetic moments of the body, okay, and all the cells in the body, which are mainly hydrogen and carbon and oxygen. And then, of course, you reconstruct your image, and there is a lot of computer powers and reconstruction elements in that. And then you are getting these very beautiful, very precise images that we now know. So we were discussing about industry, and this is what is going on today. So this is the market forecast up to 2030, so 2022, 2030. So you're really talking about quite a lot of money in market size. This CAGR means compound annual growth rate, in case you come across to that. And it has this 7.8%. This is the growth, which is really foreseen per annum. You have two dominant markets there, Asia Pacific. So, and well, this is the period that we were discussing. So the segmentation is of the two systems that I told you originally. This is high field. So we are really talking about a magnetic field of the order of several Tesla. And the main applications are for brain and neurological. So those are really the main fields. Hospital, clinics, and those are all the players that you have now on the market. So really you see quite some names. You have Hitachi, you have Siemens, you have Canon, and others. And so you really see that there is really quite a lot going on there. So this is something very new. There was this announcement, and I found it very recently. So it was last year, actually. So it has been announced. This is an incredible monster. It's really very big. It's 132 tons superconducting magnet. It will have a field of 11.7 Tesla inside almost a meter diameter and a 5 meter long volume. And so the capability is for a full body. And here you have really the difference in the quality. Do you remember we were saying the highest the magnetic field, the highest the precision of the image that you can reconstruct, 3 Tesla, 7 Tesla, 11.7 Tesla. So we are really expecting, whenever this will become available, to have unbelievable images here. And so it is 4 times more powerful than typical hospital devices. So this is definitely the future. Okay, let's go and have a look at accelerators. They still accelerate, but they can also do other things. Disclaimer, do you see this here? I don't know why it was put there. I took this slide from a very good friend of mine who is an accelerator physicist, and for some reason he decided to put this cartoon of Einstein there. I am not sure why, okay? And I don't think really, anyway, let's suppose that it's because, of course, there is something to do with, okay, well, I don't know. Anyway, I'm leaving it there, but I am innocent, so no criticism there. But for the rest, it is an amazing slide because it's really showing what you can really do with accelerator. You can produce, of course, proton, ions, electrons for proton therapy, hydron therapy, hadron therapy, which are really the two. But then you can also have operations, so you can really use it for internal operations. And very high energy electron therapy. Then, of course, you have a target. You can generate secondary beams, mainly through the production of X-ray and neutrons, both for therapy. Actually, neutrons are really quite interesting because neutrons can be captured by boron. And the boron capture, neutron boron capture, is now really very hot in on cancer therapy, because you can have normally nanoparticles with boron that you can place in regions near the tumor. Then they would capture a neutron and there would be a re-emission, normally of alphas. And alphas, you now should know, they have a very short range and therefore, and release a lot of energy in this very short range. So this is really quite a smart way to make sure the delivery of your energy, killing the cells, and we will get to the killing the cells in a moment, is really local. You don't want it to go anywhere, and in particular, no near healthy cells. So this is a smart way somehow to use it. And then, of course, you have the production of radioisotopes. And this is essential both for imaging and for therapy. So positron emission tomography, single photon emission tomographies, we will see it tomorrow actually. And of course, you have a target alpha therapy that we just spoke now. So quite a lot. And here, of course, is the number of operating accelerators worldwide, which are operating and doing this very specific type of operation. So don't worry, I wanted to enter into that just for you to have it in your portfolio, just to tell you that you have for diagnosis, either in vitro or in vivo, different type of isotope which are going to be produced. The interesting thing is for the therapy, of course, and many others, sources, systemic and blah. The interesting thing here is, of course, that all these radio emitters, they have a so-called half-life. And depending on what you are doing, the type of treatment or images or anything, you will need really to take this half-life into consideration, because you have a patient, he goes for an image, and you don't really want this person to be radioactive for much longer than what is needed. So you have that. Normally, these half-lives goes in the matter of between hours and a couple of days. You don't want more than that, of course. So common diagnostic radio tracers. So, well, for diagnosis, I already mentioned that is in vivo SPECT, is in vivo PET. And then you have this famous half-life that I just mentioned. Technetium is, of course, very strong. You have iodine, and you might recall iodine is very specific, organ-specific, and we will enter into specificity in a moment. And then you have, well, the positron emission. I will enter into that tomorrow. Right. Right, the production in Europe for those radio tracers is not so bad, but you can imagine you want to have those nearby hospitals because they need to be fresh whenever these exams are being made. And so, well, there are regions where you don't really have very many, and they will need really to travel quite long ways. And again, a look at the market is enormous here as well. And so it is growing. You can see the growth here, 9% between 2021 and 2029. So it is really quite remarkable. And North America is, of course, very strong. You have Europe, and Asia Pacific is over here. So it is growing really quite remarkable. So again, a possibility of business there. Particle therapy. So particle therapy is very strong. Proton therapy in particular has been used to treat more than 160,000 people worldwide by now. And I already mentioned that by 2030, this number is going to double, if not more, because it is extremely effective. So this is using, so first of all, those accelerator now can be bought by hospital. They come and install it. And it doesn't really take too long. So you really have companies which are making those accelerators. It can be either cyclotrons or synchrotrons. And you just phone the company, sign a contract, they come and install it. We had one installed in Manchester at the Manchester Christie's Hospital. And from the moment where they announced it, the moment where they accepted the first patient, it took 1 year. So it is really extremely fast. So 21st of February, 2023, cancer patient from Mumbai treated with proton beam therapy at the Apollo Proton Cancer Center. So it's really very, very new. I found it by chance. It is really very fresh. So a couple of days ago, and a 62-year-old man from Mumbai who was suffering from lung cancer has successfully been treated with proton therapy at the Apollo Proton Cancer Center, the first and only proton therapy center in South Asia and the Middle East. I think this is really quite remarkable, and I would like an applause. Because this is totally remarkable. So no, it's not time yet. You can, you can switch off the lights. The applause was because I think it is absolutely extraordinary, okay? It's time to go for lunch. I'll be brief, I promise. So there is some history here. Let me just tell you this story because it is really to be completed. So now that you have got one here, and so it can really save lives around. It is fantastic. Let me tell you that all this business and this adventure started in 1954 at Berkeley. And then the first lab, hospital actually, which accepted patients was in 1993. So it really took quite a long time to go from the idea to have an approval actually from all the bodies, the governmental bodies to be accepted. Carbon ions was in Japan actually in 1994. And I'll show you in a moment the difference, so it's really interesting. In Europe, 2009. And then from 2006, you have these famous commercial industries which are producing the really packaged type keys on hands devices or accelerator that can be installed in hospitals. So 80 now working worldwide, and more centers are planned in the near future. So everything, and you're probably familiar with that. Who have heard of the Bragg peak? Okay. Most of you, several of you, so I don't really need to enter into too many details. You know why this is really better. Better block, d over dx in the human body, interactions of protons, so you really need to have charged hadrons. They interact, both Coulomb interaction and then its nuclear interaction, to the point that, of course, is mediated very strongly by V over C, and since it becomes really C over V, V gets, of course, decelerated, so it gets smaller until a certain point where you have the release of all the energy. This is the principle, and so you have really these very, very precise peaks where all the energy is released. You compare it with an X-ray, and you see that these are electrons, to be more precise in this figure. And so you see that if you have something which is going, a problem, let's say a cancer, to be more directly there, inside the body with a certain depth, you are going also, if you are not using ions, hadrons to be more precise, you are also going to deliver energy to healthy tissue. You don't want that because you could be generating cancer per se. And so this is really a good way of doing. Nothing happens before a release of energy. Nothing should be happening afterwards. Unfortunately, this is not completely true. Anyway, the key words here is low dose to the healthy cells. You want to blast the cancer cells. Some of them are radiation hard, which is unbelievable, okay? They are intelligent, and they can survive radiation very, very strongly. And you just want to make sure, on the other hand, that all the healthy ones are left alone. What is happening here? Here is either proton, carbon ions, is reacting mainly with water. And then you have several reactions taking place here, to the point that you are even emitting positrons. And positrons, of course, are very interesting because you create positronium. They emit, of course, the back-to-back 511 keV, and so you can do something very interesting, which is determine exactly where this reaction took place, and so know exactly where the beam went. This is one of the ongoing problems, actually, for this type of therapies, is that they work well, but the patient is alive and therefore moves. And sometimes it is also difficult to identify. You have a person of a certain age, with a certain density, the tumor is in a certain depth. So it is, of course, done with a lot of care, the cancer treatment, but there are still unknowns. And so you really need to find a way to understand what happened to the person and what happened to the hadron that has been used to treat. What are you going to use here? Relative biological effectiveness, RBE. These guys, this is a very, very important concept that you might really see again in your life. So bear with me for another moment. What does it mean? This is how much dose you need to release to a cancer cell to kill the cell. And normally you have this ratio, which is a reference absorbed dose with a standard that you know if does a certain effects, and the dose which is absorbed by the type of radiation. So this is a very important point to remember. You know everything about dosimetry, right? I don't need to really stop here. Just, just a little reminder though, just in case. Becquerel, 1 decay per second. Curie, 37 gigabecquerel. The dose is the amount of radiation absorbed by any material. You use gray. Absorbed energy per mass unit, 1 gray is 100 rads. You don't need to know more because I'm sure you have heard that already. And we are going back to this story of the effective dose based on this radiobiological effectiveness. So how much do you need to give in order to make sure that the cancer cell is gone for good, you don't have it anymore? And here, well, there are all the various definitions that you might find one day. And so I leave it there and I leave you to read it just to make sure that if you see it, the equivalent dose is in sievert. And then, of course, you will need to take into account some important factors with this radiation weighting factor. And then it is the tissue weighting factor. And so you will have really all this formulated so you can also calculate it. Okay. Another way that is really rather smart, actually, and many people are working on that. And so several of the detectors that you have seen, in particular the one for gammas, are used for this, is the precise Bragg peak reconstructions using prompt gammas. So among all the various reactions, you have generation of positronium, for example, but also you have gammas which are being produced. And those gammas, normally you would use lysocrystals. This is an example with lysocrystals and silicon photomultipliers because those gammas are very penetrating. So you will need really the crystals. And here what happens, you have the proton beam, the generation of the prompt gamma, and then there is a beautiful study which shows that when you are comparing the Bragg peak with the prompt gammas, you see really a one-to-one correspondence. And so this is another very interesting way to make sure that, that you recognize and you identify exactly where the proton beam deposited on the Bragg peak. Different detectors, you saw several of them, and your gem trackers and scintillating fibers, very similar to the ones that you're using in your experiments, okay? So this is really something to keep in mind, okay? A system where you have at the same time a tracker, the PET scanner. Tomorrow we will enter into that, so don't worry about it. And so there is a lot of in vivo measurements that you can do with all these methods. Right, I mentioned light ions rather than protons. Protons are much easier to of course, accelerate. And these accelerators can be made rather compact. Carbon ions, though, they have many more advantages because the famous radiobiological effectiveness that we mentioned and defined before is higher for carbon ions with respect to for proton, is roughly a factor 3. And having said that, you see here what is going on. You have the proton and X-rays cause a single strand break on the DNAs of the cancer cells, while carbon ions, they produce 22 times more ionization per length, generating many more of those. And this is why carbon ions are interesting. There are a couple of drawbacks, though, and then it was observed that there are fragments which are being generated after the Bragg peak. And these, of course, needs really to be controlled and studied a little bit better. But of course, this is very interesting. Another thing that I want to mention just for completeness, because it's so new that you might be interested in knowing of this. And it is a combination of ion therapy and immunotherapy. Immunotherapy is everywhere. You are talking about personalization of the treatment, and it simply means that when you have identified some chemicals which are really reacting very well with the immune system of the person, you're basically generating some sort of a vaccine for the type of cancer for the person, because of course it depends on the DNA of the person. And then the combination of the two is definitely the future. Have a look at this paper, because it is really quite interesting to see how this is evolving. And of course, this is what we want. There are certain cancers that still today are very difficult to treat. One is pancreatic cancer. It is one of the really, what they call the killers one. The other one is the brain. And those pancreatic cancer cells, they are radiation hard. And this is where you really need to combine the two. So chemotherapy, personalized chemo, plus radiotherapy, and in particular proton therapy, to make sure that you're really getting rid of it. Another thing I wanted to mention is that in the delivery of the protons, you have different ways of doing it. And from the accelerator point of view, the holy grail today is the so-called flash therapy. Have you heard of that? Flash therapy, yes. And this, as you know, it is extremely powerful because it is very short, and in a very short pulse, you deliver all the energy. In this way, you have, of course, a much higher radiobiological effectiveness, so you blast the cancer cells, and also the patient is allowed to move because it is so short in time that you are not really suffering from the patient moving during treatment. So to keep in your radar, if you're interested in this type of things, flash. Particle therapy market just growing. The famous CAGR, 8.3%. It is really going strong, and correctly so. And with these new ideas, these new ways of controlling it and flash, I think we are really entering, and of course, the chemotherapy personalized, we are really entering into a new era where probably in the next, where they are talking about 10 years, maybe, we might really be able to control. Eradicate, I think, is strong, but control several of the cancers. They are still killing a lot of people. Right, so, okay, we are really getting closer to the end. You would be pleased, yes? And since, just because I have a few minutes, I'm not even sure I'm going to use it. I just wanted to mention and show you these beautiful pictures about the civil engineering. Since we will hear more about dark matters and neutrino, we heard this morning, we have, of course, the XXL cavern installations. And so all this is benefiting from all the knowledge and know-how. And then, of course, you will have other application gravitational waves, environmental monitoring, very strong for climate change. And it's very close to my heart. And I'm getting very involved now with climate change because there is a lot that we can do. And here, of course, this is one of the ways. And yeah, data acquisition system, just a couple of slides. We mentioned, so the International Data Corporation estimates the amount of data in the world will reach 163 trillion gigabytes by 2025. And so storage and share will be an issue if we don't do something about it, right? So medicine, satellite space, astronomy, and so forth. So all our close colleagues, proteomic and genomics still. And so the Swiss Institute for Bioinformatics generates up to 30 terabytes a week in DNA sequencing. And so really quite a lot of stuff. And of course, we have the synchrotron and the Blue Brain project. I just put it there because since it's biomedical, this project is being started, of course, to try and simulate using a computer the functionality of the brain. And it is not only with the attempt of understanding what is going on from the chemical point of view, but as you can imagine, the idea would be to put together enough nodes and neurons. Of course, those are we're talking about electronic ones, to be able to see if consciousness can be generated. And of course, it is really quite a difficult one, as you can imagine. Data simulation. Again, there are really quite a lot going on. I'm going to mention few, but finance has been profiting a lot, and biologic, and so forth. Who is using GM4? Here. Right, so some of you are. What is interesting is that GM4 has been, of course, drifted or has been transferred into medical application very strongly. GATE is the GM4 application for tomographic emission. So a lot going on, you can do really quite a lot of that, and you find a lot of resources online, but there is an artificial intelligence in GATE, and so there is really quite a lot. This is very, very new. It is really, of course, as you know, trying to enhance the capabilities of GM4. But I wanted to get to this package. Who heard of that? Topaz. Okay, so some of you have. And the reason why I want really to stress that is because you can do two things if you are interested. The first one is that it's online. It's official, it's online, and it is free. You can go and download it. You register. My student did that, and I did that too, actually. You just go there, you download, and you follow courses online. And those are really specialists. It's again derived from GM4. It is much simpler, and you can do a lot of the functionalities. It has really been done for radiotherapy, okay? And model X-rays, particle therapy. So you can really, if you have a detector, you have all the type of detectors, all the geometries that you can create, and you can really see the effect of a detector for particle therapy. So here, just to close Beauté, as we would say, if I manage. Oh, no. Wait. Okay, so this is a very simple cylinder with some particle being generated. And so you have all that being generated, and it's free, and you can learn really quite a lot if you're interested in simulation. And so I'm stopping now for today. And so detectors tomorrow.
I am only saying that here not the GN4 user, GN4 developer is also here.
Of course.
Yeah.
Of course.
Now, question.
Thank you for the presentation, ma'am. You talked about the NMR imaging. So since we have so many cells in the body and every single cell has its own alpha beta, how do we actually manage to measure for particular area, alpha and beta? How do we localize the effect?
Right, I think it is a very good question, of which I don't know the details because I have never done it myself. But I have the impression that it really looks at regions, and there is a lot of computations. On the other hand, I think it is really looking at a particular region. So you are looking at structures anyway. So you are really to be able to identify the differences in the different structures in your brain. The brain is really one of the best, of course. You need the water there. It is really working a lot with water. And so it is targeting the water, which is in our cells, and in the differences actually in the different regions. So I think this is the way it works. Rather than looking at the single cell, it looks at groups of cells, because our body works with group of cells in our structure, if you think about it. And so it is really the difference between the two. And I stop there because that detail I don't know.
Thank you.
I have a question about the biological effect of flash radiotherapy. Is it understood how could the delivery of a very high dose in very short time, treat cancer without touching the surrounding areas? Is this understood?
So let me see if I understood your question, because it is not really, there is some echo. So you want to know the radiobiological effectiveness. So if you can really understand if cancer is being beaten, so it's being
Yes. Well, I mean, yeah, the biological effects. How does it work? Why does it treat cancer without touching the surrounding area?
How it works. So this is all the trick, actually. So this is why you're really looking at methods by which radiation goes through without interacting. And we know that if you have a penetrating radiation, it goes through without interacting, right? Mm-hmm. It is really down to the interaction of particles with matter. We know that when you have certain type of particles, X-rays, for example, so X-rays, they have, of course, a certain penetration depth. So we know that they can either go through or they can stay inside. But you will never know where they are releasing their energy. You know that it is a point-like release, but you don't know where. So this is really a statistical process. So you have a stochastic process in which X-rays are releasing their energy, which is not the case, for example, for protons. dE over dx, the formula of Bethe block. You know that you have a so-called linear energy transfer, also said in the medical field. And so you know that you have a certain energy transfer within a certain distance. But this energy transfer, when your proton has a certain energy, is very, very little at the beginning, because you only have a Coulomb interaction. It's only becoming important when the beta, the famous 1 over beta square, start playing a role. And so you have V over C, okay? And so it is on the denominator. And so when you put it on the numerator, then you have a C over V. And this is the key, because when you have these interactions with Coulombic, so it is really with the external electrons, and this slows down the particle inside the body until the point in which this V is really get closer to zero. And so you see at that point that the dE over dx, you have a proportionality, there is a lot of stuff also. But this is where the energy gets the largest. And this is the key point. So this interaction is not destroying anything because the particle is just going through, getting slowed down by the electrons of all the of all the ions that we have in the body, until the point in which they are almost stopping. So the particles which are coming in, protons, are almost stopping. But when they stop, they need to release all their energy. And this is the key. Okay, the other method that I mentioned before is neutron. Neutron goes through you. And of course, it depends on the energy. We really have to be taking. But then you have elements which are capturing neutrons. Of course, it goes through, by the way, the body because there is no interaction, Coulomb interaction. So you really need something to stop the neutron. So you really need the neutron either is captured by a nucleus or it is trapped by very effective neutron capture material like boron. And this is why you would put boron where the cancer is, because you know that all the rest of the neutrons, they would go through the body, we don't do anything. But those who are stopping in the boron, they will go through a nuclear reaction by which you will have an emission of a gamma, a neutrino, by the way, and you will have an emission of alpha. And this is what you want. Alpha, you might remember, is having a range which is very, very short, very short. Even in air, it's very short. So when you have matter, it's ultra short, and it releases a lot of energy. And this is what you want, because of the radiobiological effectiveness. Is it clearer? Right, so you have really ways coming from nuclear physics, which nuclear physics fundamentally, which allows you really to optimize. Some energy is always released, but it is not damaging. Not damaging as much, a little maybe, but not as much as X-rays, for example. So I have to say that, yeah, probably there is really nothing going on. In particular with proton therapy, neutron even more, on the cells which are in front the target.
Okay, any more questions?
With proton or ion therapy, we see the energy diffused by the charged particle follows a back curve. And the back peak where the most of the energy of the particle is deposited in the body.
Correct.
So but near the tumor or the cancerous cell, which I want to destroy, there are healthy cells nearby. So, and the peak has is not very sharp. So that may affect the neighboring healthy cells also. So how to reduce this? Is there any way that this peak can be resolved more such that the neighboring healthy cells are not affected? Or
Right, this is a very good question. So this Bragg peak can really be very sharp. And normally a tumor is not really a single point. Normally what happens is that the position inside a body, water, basically, can be determined very precisely by energy. So is dA over dx. And so what is being done, you have different type of methods, but the one I have in mind is some sort of a pencil beam, which is just going around the volume. And so you can move it around with the magnets just for a plane. So if you have let's suppose that this is not. Let's suppose that, oops, no, even. Let's suppose that this is the cancer, okay? And so you have really a volume here. It is three-dimensional. And so the beam is going to be moved, if it's coming in this direction, is going to move on a plane. And the energy is what is giving you the depth through the volume, okay? And so there is, when they prepare a cancer treatment planning for the patient, they just do exactly that. So they tackle the patient in different direction, and they just deliver pencil beams to different points to cover the area at different energy, and so you have the depth. So all these can really be done in such a way that you have a precise scalpel. They even call it the scalpel. Finally, this entire story today works very well, saves your life. But then we really need to wait to see in action is the famous flash that we were discussing before, where you will have that the beam is slightly bigger, and then it will just release energy in one shot. And then the energy will be a little bit increased, and so the shot will be released a little bit further. So, but anyway, you will have really a lot of energy being released in one single shot, because this is really the most effective way. But it is really very, very precise. The way the Bragg peak is operating, in particular with the carbon ions, extremely precise. So there is quite a good job that you can do there, preserving the cells around it.
Okay, I think with that answer, thanks, Cinzia, for this talk. And
Thank
we
you.
have more to come on tomorrow.